Let us look at the perspective view, which is the view that we see with our eyes and cameras. In orthographic projection, the camera's focal length is considered to be infinite. That means everything that the camera sees in front of it will be projected on its plane orthogonally. The perspective projection, the camera's focal length d is finite. So the difference between orthographic projection and perspective projection is that in orthographic projection the focal length is at infinity, which you can also consider that the camera lens is placed at infinity, whereas in perspective projection the focal length is a finite value, say d. D is where the camera's imaging plane is placed. Now in this diagram we have a simple perspective projection. The center of projection is the origin. The projection plane is at z is equal to d, where d is less than 0, which means d is ahead in the negative z direction. Now looking at the top view of the previous diagram, we see the xz values of the point projected on xp d of the projection plane. Now projection is done that every point is sort of drawn in a straight line towards the center of projection, and wherever it crosses the imaging plane is the location of its projection. So this is the top view. Now because this angle is the same for this point and this point, we can write that the relationship xp over d, which is the location of this point in the projection plane, is equal to x over z, which is the actual location of the point in the real world. So this ratio would be the same. xp divided by d is equal to x divided by z. Now looking at the side view of our projection from the previous slide, the yz value of the point in the real world would be projected to ypd while drawing a straight line to the origin, which is the center of the projection. And this is our projection plane now. Now again, because this angle is the same for this point and this point, the ratio yp divided by d from here would be the same as y over z from here. Now rewriting this equation, we can find the value of our projection, x projection point equal to x divided by z over d. So it's just taking the d down here and gets divided by the whole term, right? The same goes for yp. Yp is equal to y divided by z over d. And what would be the zp value? Well, everything gets projected on the d plane, and hence zp is equal to d. So this is from our synthetic camera model that we studied in our previous. Now the projection matrix of a simple perspective is given by M, right, which has one value for the x projection, one value for the y projection, and then one over here, and a 1 over d over here, which, and remember that d is the location of the projection plane. So if we multiply a point P with this matrix, we get this projected value Q. So if P is x, y, z, 1 in homogeneous coordinates, its projection Q would be given by x, y, z, and the last value would be z over d. In OpenGL, this term is called W, and this is the perspective division. Now in homogeneous coordinates, we would want this value to be 1, and hence we'll have to divide all these values with z over d. So since W is equal to z over d, which is not equal to 1, so we must divide W by the result to get back to the homogeneous coordinates. And doing so, we will get xp value equal to x divided by z divided by d, and yp is equal to y divided by z divided by p, which is again So division of these values by W. And of course ZP is equal to W straightforward, which is the location of the projection plane. Now applying the projection matrix and getting back to homogeneous coordinates gave us exactly the same equations that we saw in slide 3. There is an easier way to get the perspective transformation matrix by using the core library GL frustum function or the frustum function from met.h, which will return a 4x4 transformation matrix which you can combine with other matrices to get your final transformation, or you can use it directly to perform perspective transformation. The input arguments to the frustum function are the same as were for the orthographic view function. However, it is used differently here. The center of projection is at 0, 0, and depending on how these arguments are defined, you'll get a orthographic view frustum. The left, right, bottom, top values are always defined for the near plane, and the near plane is at minus near value from the origin. This is because the camera is looking at the negative Z direction. So while the near argument is positive, it is inverted to form the near plane. And depending upon how far you define your far plane, this will keep the X, Y, and bottom top values will keep increasing. But you don't have to worry about that, because just by defining these values for the near plane, the left, right, bottom, top values for the near plane and the near and far planes themselves, you will get a perspective transformation matrix returned to you. The GL frustum or the frustum function, it is often difficult to get the desired field of view. Another way to get the perspective projection is using the perspective function, which takes the field of view in the y direction as an input parameter. This is defined in mat.h and returns a 4x4 matrix. An equivalent function is defined in the glue library, which is called glue perspective. FOVY is the angle that specifies the field of view in degrees in the y direction. Aspect specifies the aspect ratio that determines the field of view in the x direction. The aspect ratio is the ratio of x, which is width, to y, which is height. The Z near specifies the distance from the viewer to the near clipping plane. It is positive. Z far specifies the distance from the viewer to the far clipping plane. This is also positive like before. All values are passed as GL floats.